This lecture covers the probabilistic analysis of algorithms. Here's a roadmap of what we will cover. In this lecture, we will conduct the average case analysis of Quicksort and use it to discuss the probabilistic analysis. After that, we will cover a variation of Quicksort, the randomized Quicksort, and use it to deepen your understanding of probabilistic analysis. In the Part 1 lecture, we covered the Quicksort algorithm, the worst case time complexity analysis, as well as the best case analysis. In this lecture, we will start by covering the average case time complexity analysis of Quicksort. On the screen, you can see and compare the two recurrence tree structures of the worst and best cases. As you can imagine, the time complexity of the average case will be somewhere between the two. By saying that, I mean the upper bound of the average case should be bigger than or equal to the best case and smaller than or equal to the worst case. Given an arbitrary array as the input, it's highly unlikely that the array has the characteristics that fits in either the best or the worst case. There's some randomness being involved. To account for the randomness, we need to approach analyzing the time complexity of the average case a little bit differently. We would call this approach the probabilistic analysis. A comparison between the time complexity that you are familiar with and the probabilistic analysis is listed on the screen. The regular time complexity analysis, as you already know, doesn't assume randomness in the input and focuses on defining the characteristics of the input so that we will have the best, worst, and the average cases. In contrast, probabilistic analysis focuses on using the expected performance over all possible random outcomes to account for the randomness in the input. The one thing that we need to highlight here is the expected performance. It's a probability concept that we may need to refresh your memory on. In fact, there are three concepts that I want to make sure that we are all on the same page, including the uniform distribution, expectation of a random variable that's used to measure the expected performance, and the linearity of expectation. Let's go through them one by one. So what's uniform distribution? A random variable x is said to follow a uniform distribution if all outcomes are equally likely to happen. For a random variable x taking in discrete outcomes, assuming that each would happen with equal probability, then the probability will be 1 divided by n. Let's use an example to demonstrate the concept of uniform distribution. When you roll a fair 6-sided die, the possible outcome ranges from 1 to 6, right? Because it's a fair die. So the probability of the die landing on any side is the same, which is 1 divided by 6. Okay? The next concept is the expectation of a random variable. We mentioned that it's used to measure the expected performance of randomness. So how is that really defined? The expected value of a random variable measures the central tendency that the random variable takes. So it's a weighted average of all possible outcomes, where the weights are the probability of those outcomes. The way to compute the expected value is to sum up a set of terms. Each term is the product between the random variable and its corresponding probability. Let's see a few examples of expectation. The first example is still about rolling a fair 6-sided dice. The expected value of this action is computed as 3.5. How is that done? So you will sum up a set of terms, and each term is the product between a random variable, or say the outcome, and its corresponding probability. In this case, the probability of each outcome is the same. It's 1 divided by 6. The ending result is computed as 3.5. Okay? For another example, let's think about buying a lottery ticket. Assuming that the ticket has a 1% chance of winning $100 and 99% of winning nothing. The expected value of this scenario is the sum of the two terms. The first term is the product between 100 and 1%, and the second term is the product between 0 and 99%. So the ending result is simply 1. From these two examples, you can see that the expectation is computed as a weighted average of all possible outcomes, where the weights are the probabilities of those outcomes. That's how you measure the expected performance of randomness, which will be critical for us to account for the randomness of the pivot value given an input array for the quicksort algorithm. So the last concept we need to refresh your memory on is the linearity of the expectation. Just to be sure, the expectation here is exactly the same concept as we just discussed. It's computed as the weighted average of all possible outcomes. So the linearity of expectation is defined as the following. The expectation of a sum of random variables is equal to the sum of their expectations. For example, if you have two random variables x1 and x2, the expectation of x1 plus x2 is the same as summing up the expectation of x1 as well as the expectation of x2. Additionally, you may also want to know how to deal with the constant number that's multiplied to your random variable. For example, if you have a constant number c, then the expectation of c multiplied to x1 is a random variable, so this expectation is equal to c multiplied by the expectation of x1 itself. In short, you can extract the constant number out of the computation of expectation. Let's see an example. So this time, you're rolling two 6-sided dice. Of course, each dice is a fair 6-sided dice. If we use x1 and x2 to represent the outcomes of the first and the second dice respectively, we will be able to know that the expected value of both dice are the same, which is 3.5. This is the same thing as we just computed. The possible new thing here is the expectation of x1 plus x2. Well, that's equal to the sum of the expectation of x1 and the expectation of x2, which will give you 7. Now you know the three probability concepts. We will see their application in how we go from the recurrence relation to the time complexity function for the average case of quicksort. Instead of deducing the recurrence relation of the average case from scratch, I'm going to give it to you and try to make sense of it together. So here is the recurrence relation of the average case for quicksort. Same as all other recurrence relations, a recurrence relation is composed of two parts. The work done at the current step and the work done in the recursive step. The n-1 here represents the time it takes to execute the partition method at the current step. From the part 1 lecture, you know that the partition method, as a helper method to the quicksort, traverses the input array for one time, so it takes linear time to get the job done. The other clumsy term represents the time it takes in the next step when the recursive calls are triggered. It is the expected value of the cost of the recursive calls. An obvious question that you may ask here is where the k comes from, or what is that? Well, the k represents an arbitrary position in the range between 0 and n-1. The position k here is the split point, or say the index of the pivot, after the partition method is executed. In case if you don't know what I'm talking about, you need to refer to the part 1 lecture. So where do you think the split point will land? Anywhere? Yeah, anywhere. Each of the n positions can potentially become the split point because we assume that the input array is randomly ordered. As a result, the possibility of the split point landing at the particular index k is equal to 1 divided by n. That's where the 1 divided by n comes from here. Next, what about t of k plus t of n minus k minus 1? What does that represent? Well, you know that k represents an arbitrary split point. If you execute the quicksort algorithm, what you will do next when you get a split point? You will trigger two recursive calls. One on the left subarray of the length of k, the other on the right subarray of the length of n minus k minus 1. Okay, so t of k here represents the time it takes to run quicksort on the left subarray. And similarly, t of n minus k minus 1 represents the time it takes to run quicksort on the right subarray. If k happens to be at the middle point, you will end up with 2t of n divided by 2, which you have already encountered when we covered the best case time complexity analysis of quicksort. To account for the randomness, one thing that we need is the arbitrary position k. Okay? The other thing is how to represent the time it takes to trigger the recursive call. We used the expected value here to do so. The expected cost, or say the expected time it takes in the recursive call, is computed in the same way as other expected values by adding up a set of weighted terms. Each term is the product between the probability of the split point landing at index k and the time it takes to run the recursive calls on its left and right subarrays. Okay? The probability is the weight whose value is 1 divided by n for each random variable k. In relation to the term of expected value dominated by k, 1 divided by n is a constant number, so you can extract it and multiply it to the summation. That's why there's a difference between what you see in the recurrence relation and what you see at the bottom of the screen. The two terms are interchangeable. Now you know what the recurrence relation is composed of for the average case of the quicksort. How do we get from here, the recurrence relation, to its upper bound? Besides the recurrence tree method and the master theorem, we will attempt a new method here that's called the substitute method. Different from the recurrence tree method and master theorem that we covered in the past, the substitute method starts by making an educated guess on the upper bound, and then moves to prove the guess via induction. For example, given the recurrence relation of the average case for the quicksort we just covered, we can make an educated guess, which is the upper bound of the corresponding time complexity function is big O of n log n, expressed as Tn. The time complexity function is smaller than or equal to c, which is a constant number multiplied by n log n. Okay? So that's the first step in using the substitute method. The second step is to prove this guess via induction. If we can prove our guess is true, then we will be able to establish that the upper bound is simply big O of n log n. If we can't, we need to go back to step 1 by making a new guess. The key here in using the substitute method is induction. In case if you forget what it is, here's a common example that can help refresh your memory. Let's forget about the average case upper bound for now and focus on this example on the screen. Okay, it's all about induction. Assuming that we made a guess and want to prove this math formula, Sn, defined as the sum from 1 to n, 1 plus 2 plus 3 plus all the way to n, where Sn is equal to n multiplied by n plus 1, then divided by 2. We want to prove that this formula holds for all the numbers of n. and we will do so by using induction. There are 3 steps that are involved in this process. Similar as what you do for recursion, you need to prove the formula holds for the base case first. For example, when n is small enough, and so the case becomes very trivial. When n is equal to 1. Sn, or say S1, can be expressed as n multiplied by n plus 1, then divided by 2. You can simply replace all the n's with 1, and you can easily tell that, well, this formula holds for the scenario when n is trivial enough, when n is equal to 1. The next step is to assume that the given formula holds for an arbitrary given number k, so that in the third step, you can prove that when the arbitrary number is 1 unit bigger, the formula still holds. In other words, you need to prove that s of k plus 1 is equal to k plus 1 multiplied by k plus 2, then divided by 2. You will get the job done by using the assumption you have established in step 2. Essentially, s of k plus 1 is equal to s of k plus another unit, which is simply k plus 1. Based on the assumption you have established in step 2, sk can be replaced with k multiplied by k plus 1, then divided by 2. All it remains is to build a connection between these 2 steps. I'm talking about these 2 steps, or say, prove that they are equivalent to each other. In short, induction involves these 3 steps, starting with proving the base case. Then assume that the claim is true for an arbitrary number. In the end, you need to prove that the claim holds when the arbitrary number is increased by using the help of the assumption. For our case, I mean the upper bound for the average case, will be very similar. The first step is about proving the statement holds. In the base case, when n is equal to 1, the array size is 1, so the quicksort doesn't even need to run at all. So t of 1 will be smaller than or equal to 1 multiplied by log 1, which is also 1. So that said, the base case is proved. The second step is to assume the statement holds for an arbitrary input size such as k. As we do that, we will also try to simplify the recurrence relation a little bit by assuming that k and n minus k minus 1 tend to have similar sizes, considering that it is rare for either the best or the worst cases to happen frequently, so that the expected value term can be simplified to 2 divided by n, and then multiplied by the sum of tk, where k ranges from 0 to n minus 1. We will assume that when the input size is an arbitrary number k, we have t of k that's smaller than or equal to c multiplied by k log k. Okay, that's the second step. The third step is to prove that the statement holds, based on the assumption that we just assumed at this step. We already have the simplified recurrence relation between Tn and Tk. The recurrence relation provides a way for you to know how input size increases as recursion is triggered. It goes from k to n, where k is an arbitrary number between 0 and n minus 1. Beyond that, we have the help from the assumption that we made at step 2. tk is always smaller than or equal to c multiplied by k log k. When we plug the assumption into the simplified recurrence relation, I mean to replace t of k with c multiplied by k log k, you will have a Tn that's always smaller than or equal to n minus 1 plus 2 divided by n, then multiplied by the sum of ck log k. If you still remember what you learned from calculus, you will know that the summation term can be approximated to its corresponding integral. Based on that, you can calculate its antiderivative as is shown here. K is an arbitrary number between 0 and n minus 1. As such, this term is going to be smaller than its counterpart, in which k is replaced with n. These concepts in calculus are beyond the scope of this lecture. If you forget what you learned or need to catch up with calculus, you can search for integra and antiderivative or ask a relevant question to a generative AI tool. That said, this step allows you to replace the summation term with the antiderivative where k is all replaced with n. Like this. Now, Tn is smaller than or equal to this formula, where k is all replaced by n. After some basic calculation, you can get rid of the constant number c, and deduce that Tn will be smaller than or equal to n log n. In other words, we have proved our guess via the induction method. The upper bound of this time complexity is big O of n log n. Given a randomized input array, the average case of quicksort runs on big O of n log n. Note that the assumption of a randomized input array is important, because it means that hitting the best or worst cases would be very rare. However, if the input array is not randomized, the weakness of quicksort is still noticeable, because the pivot is chosen using a deterministic approach, such as always going with the first element or the last element. If the input data is already sorted or nearly sorted, a deterministic pivot selection can lead to highly unbalanced partition, resulting in the worst case. So that's where the randomized quicksort algorithm comes into play. And that's exactly our next topic. Randomized quicksort aims to minimize the chance of hitting the worst case of quicksort when the input array is not ideal. So what does randomized quicksort do? Well, it does everything the same way as the regular quicksort algorithm, except for randomly selecting all the pivots. You can implement it in many different ways. One possible approach is to randomly select an element in the subarray and then swap it with the first element. After that, you can stick to using the first element as a pivot. If you go with this approach, you only need to change a few lines of the pseudocode in the implementation for the regular quicksort that we have shown to you. So this is the implementation of the regular quicksort, where the first element is used as the pivot. To change it to randomized quicksort, you will randomize the pivot every time as the first thing to do in the partition method. The helper method, named randomize, will choose an element randomly in the subarray, then swap it with the first element. The remaining code will stay exactly the same. The algorithm itself is not hard to grasp. What's the time complexity of the randomized quicksort? Instead of doing the analysis by tracking all the details, we will distill its time complexity to the expected number of comparisons performed by the algorithm. Why can we do that? Down to its core, randomized quicksort is still about comparing the pivot to every other element in every recursive calls. That said, the main computational cost in quicksort arises from comparing elements to the pivot during the partition process. In case you forget, this is the pseudocode of the randomized quicksort. The process of randomly picking an element and then swap it with the first element costs constant amount of time. So that said, the biggest cost comes from this partition method here, in which you compare the pivot to every other element in each of the subarrays when quicksort is triggered recursively. Okay. Because the main computational cost in quicksort comes from comparing elements to the pivot during the partition process, focusing on just analyzing the comparisons avoids the need to explicitly tracking other details of the algorithm. Given these reasons, if we can figure out the number of comparisons performed in randomized quicksort, we will be able to establish the total runtime, because the total runtime of quicksort is proportional to the number of comparisons performed. Remember, we are still dealing with the expected number of comparisons. The emphasis should be on the expected number that accounts for the randomness nature of this algorithm. To get the expected number of comparisons, we need to figure out a few things. The first is the probability of the comparison between two arbitrary elements in the input array. Let's use I and j to represent the two indexes of the two arbitrary elements. For the two elements to be compared, they need to be in the same subarray, and either of the two needs to be selected as a pivot. For a subarray to contain both elements at index I and j, the subarray needs to at least start from I and end at j. To express the probability of this scenario, we can use a formula like this. The probability of this scenario can be broken down into two different probabilities. The first is when element I is selected as a pivot, and the second is when element j is selected as a pivot. In the subarray starting from I and ending at j, each element stands the same chance to be picked as a pivot. So the probability of picking element I will be simply 1 divided by j minus I plus 1. The same thing can be said for the probability of picking element j. And just to be sure, j minus I plus 1 represents the size of this corresponding subarray. As a result, the probability of this scenario can be computed as 2 divided by j minus I plus 1. Here, we used some concepts from probability theory, in case you never learned or forget such things. You can search addition rules for disjoint events, or you can read more about it, or ask a relevant question to a generative AI tool. In short, when two events A and B are mutually exclusive, the probability of either A or B happens is equal to the probability of A plus the probability of B. The probability is a vital part in computing the expected number of two arbitrary elements being compared in a given array. Next, the expected number of comparisons. We need to figure out the total number of pairs composed of two arbitrary numbers at index I and j. Why do we need that? Remember, the expected number is computed as the following. It is the sum of a set of terms, and each term is a product of a random variable and its corresponding probability. The random variable here is simply always 1 because it represents the event of comparing two numbers. It doesn't have different values. We have figured out its corresponding probability already. All it remains is how many pairs there are, or say how many possible combinations of index I and index j there would be, given an input array. If you remember what you learned from the set theory, you may know that the total number of pairs can be computed by multiplying n with n minus 1, then divided by 2, assuming that the total number of elements is n. You can also express this mathematically. All it takes is to pick an arbitrary element from the input array first, then after that, pick another arbitrary element from the remaining elements. This can be expressed as a combination of two summations, like this. The outer summation iterates over all possible starting indexes of I, which starts from 1 and ends at n minus 1. The n minus 1 accounts for the pick of the next element j. The inner summation iterates over all possible sizes of subarrays starting at I plus 1 and ending at n. You can also think this combination of the two summations as an embedded for loop. So the outer for loop corresponds to the outer summation that iterates from 1 to n minus 1. And the inner for loop corresponds to the inner summation, iterates from I plus 1 to n. Like what you see here in this box. The two summations compute to the same number as the total number of pairs, or say that embedded for loop run at the same amount of steps as the total number of pairs. It's just a different way of expressing the same thing. Now you have everything you need to compute the expected number of comparisons. The result looks like this. Here, we use C of n to represent the expected number of comparisons in relation to the input size of n. T of n is in proportion to C of n. So as soon as we figure out the upper bound for C of n, we will know that the upper bound for Tn. Let's get started. The first thing that we will do is to simplify C of n. I mean, to replace j minus I plus 1 simply with k. J minus I plus 1 represents the size of the subarray that contains elements at index I and j. The simplification allows us to use k to represent the size of the subarray. Next, we will approximate the inner summation using the harmonic number. In short, the inner summation is approximated as log base of natural number of n minus I plus gamma, where gamma is a constant number. The constant number can be easily dismissed when our goal is to figure out the upper bound. That said, the inner summation can be replaced by log base of natural number of n. The outer summation can be simply replaced with n multiplied by whatever comes out from the inner summation. As a result, C of n can be expressed as n multiplied by log n. In case if you don't know or forget the harmonic number is defined like this. The nth harmonic number is defined as 1 plus 1 divided by 2, then plus 1 divided by 3, and plus all the way until 1 divided by n, which can be approximated to log base of natural number of n plus gamma, where gamma is a constant number. You can read more about harmonic number or ask relevant questions to a generative AI tool in case if you have never learned it. Okay? Now we have the approximation for C of n. Given that T of n is in proportion to C of n, and log base 2 of n grows at a faster rate than log base of natural number of n, so that we can replace the base of natural number with the term that we are more familiar with to derive the upper bound as n multiplied by log n. That said, the upper bound of randomized quicksort is n log n. The randomization process basically rules out the likelihood of the worst or the best cases from happening. Due to its nature in randomness, we have to resort to the expected value to represent its time complexity. In this lecture, we covered the average case time complexity analysis for quicksort and the randomized quicksort, as well as its time complexity analysis. We introduced a new method to derive bounds, especially the upper bound of a given algorithm, which is the substitution method. Most importantly, we introduced the probabilistic time complexity analysis that uses the expected number to account for randomness. That's all we have, and I hope you learned something new.